So last time we saw that the equations of motion of Chern-Simons theory tell us that the field strength is 0. So let's contrast with Yang-Mills theory. We're in dimension 4. So if A, B are space-time indices, and for simplicity, I'm going to take the group to be U1. Then the equations of motion of Yang-Mills theory are, firstly, the Bianchi identity, that the de Broglie operator applied to the curvature 2 form vanishes. So this equation is obvious. So you might not normally think of it as an equation of motion. It's just a corollary of the way we've presented Yang-Mills theory with the fundamental gauge field. And the second equation is the Yang-Mills equation. That certain derivatives of the curvature vanish. So actually, let me write this like this, ABC. So you notice that this equation depends on the metric, because we use a metric to raise and lower indices. The question?
No, it was just why it was f of a is equals d to sorry. It was U1, you pick U1.
Yes, U1, exactly, yes, sorry. I'm introducing this for a reason. There's something I want to discuss in a minute. But again, just for general knowledge, I want to explain another way of thinking about this equation, which is in terms of something called a Hodge star. So 2 can be rewritten as follows. So we define a new 2 form, star f, by saying that star f AB is equal to f c d epsilon a b c d c d e f. EF, and then I'm going to lower indices here using the metric. So I'm mostly including the metric indices just to point out that this depends on a metric. We can use GAB is delta AB to simplify things. We just work on Minkowski space or Euclidean space. Okay, then equation 2 is D star F is equal to 0. So this is a nice formulation of the Young-Mills equations. Well, in this case, it's the Maxwell equations because it's the group U1, because there's this beautiful symmetry between F and star F. They both satisfy the same equation. So in Young-Mills theory, there are local operators. So for G is equal to U1, then the value of F A B at a point of space-time this is a gauge invariant measurement. So one way to say what we're describing is that for the group U1, if you like, you can think of Yang-Mills theory as not a theory of a one form, but a theory of a two form, which has no, instead of thinking of it as a one form with some gauge symmetry, you can think of it instead, there's a theory of a two form with no gauge symmetry. So we can just measure the value of that two form at a point, and that's a gauge invariant measurement. For an arbitrary group, say UN, then the value of, like, say, a trace of f wedge f, e.g., at a point is gauge invariant. For the group UN, this quantity is not gauge invariant. It lives in the adjoint representation. But if I take the trace of products of these quantities, I get a gauge invariant local observable. So there's lots of local point-like measurements. Okay, questions? So for Chern-Simons theory, it is very different. There are no local measurements. So locally, the fact that f of A is equal to 0 implies for any A, we can use a gauge transformation to set A equals 0. For example, if G is U1, A is a one form on some ball, say some R3. If dA is equal to 0, well, this is the curvature. The question of whether A is D of something is then a question of cohomology. Since the first cohomology group of R3 is equal to 0, A must be D chi for some chi. And then that means that A is equal to E minus chi d e to the chi, so that this gauge transformation trivializes A. Okay, so what we're finding is that on a small region with no interesting topology, every field configuration satisfying the equation of motion is gauge trivial. So on shell, there are no measurements we can make. Okay, any questions? Okay, so you might be wondering, well, does this mean Chern-Simons theory is a totally empty theory? And the answer is no. Although it has no measurements that can make it a point, there are extended objects which play a very important role both in Chern-Simons theory and Yang-Mills.
Can you just remind me where the RP came in?
Oh, I said, so this is like a local thing. So locally on some three-dimensional ball.
Oh.
So this is not true on an arbitrary three-manifold. There are measurements if the manifold is interested in cohomology. And these will be related to the Wilson lines.
Sir, why you take the exponential map?
Here, because this cohomology argument tells us A is d chi.
Yes.
But the definition of gauge transformation is x inverse dx. Mm-hmm. So this is not a gauge transformation. But this is a gauge transformation.
I see.
And if you apply d, you're differentiating once, so the exponentials cancel and I get a d chi.
And this argument will still be true for non-abelian groups.
Yes, but the proof is not as easy, but it's still true for non-abelian groups. For non-abelian groups, you find, you want to write A equals x inverse dx, given that f of A is 0. You think about, that's some differential equation for x. It's a differential equation on a matrix valued field. And then you think, can I solve that equation? There's some integrability constraint, which is that f of A is 0. So some kind of fairly standard results in PDEs will allow you to do the non-abelian case. It's a little more tricky. Now suppose that we have a manifold M, a three-manifold, and K inside of M is a circle. And give it like K of theta. Okay. Then, well, it turns out that although there's no point-like observables, there are observables that you can build by averaging your gauge field over this circle, and these observables are not trivial. So let's take d equals u1 for now. Then we define the Wilson line, the Wilson loop, operator to be the function of A which sends A to the exponential of the integral from theta equals 0 to 2 pi of, so we're integrating A over this circle. Okay, so this is gauge invariant. So there's a couple ways. One way to see this is, we can just explicitly see what happens if I apply a gauge transformation there. If we send A, it's sent to x inverse dx plus A. This gets sent to and then I multiply by the exponential of the integral theta equals naught to pi x inverse del theta x theta. So here, because the group is U1, x of theta is an element of U1. So there's kind of two cases to check that this is gauge invariant. So the first thing to check is, suppose that x is close to the identity. Well, then, the logarithm of x is continuous with no branch cuts. And then the integral of x inverse del theta x is the integral of del theta log x is equal to 0, as log x at 0 is equal to log x. Okay. So there's a slightly more subtle thing, is what if x winds around the circle a bunch of times? Which means there's a branch cut in the log. So if log x has a branch cut, well then, log x at 2 pi minus log x at 0 is 2, well, the branch cut in log is always integral. This is 2 pi I times n, so this disappears when we exponentiate. Okay, so described, this is how this expression gives rise to a gauge invariant measurement. And we see that if we want it to be invariant under large gauge transformations, it's essential that it's exponentiate. But if we only worry about a non-compact group, for a group as OR instead of U1, then we don't have to worry about that. Okay, any questions? So let me say another way of understanding Wilson lines. This should remind you a lot of the way we understand the Chern-Simons action as an integral of a four manifold with boundary. turns out in the abelian case, the action for a Wilson line can be understood as the integral of a surface which bounds that knot K. So the alternative is choose some sigma inside of M, which is a surface of dimension 2 with the boundary of sigma is equal to K. Now, and this might not always exist, depending on the topology of our manifold, but let's suppose for now that it exists. Then the Wilson line is the exponential of integral over sigma of the curvature. This is again special to U1. Well, this is obvious as the integral of sigma of f of dA is the integral over boundary of sigma of A. So from this picture, you might ask, why is it independent of the choice of surface? Why is this not an operator living on the whole surface? Well, if we vary sigma a little bit, to say sigma prime with the same boundary, then hold on a little picture. There's sigma, and there's sigma prime, some kind of wiggled version of it. Then, kind of like our analysis of Chern-Simons theory, the difference between these guys vanishes because the curvature is a closed two form. Let me see. Where sigma, where I've glued them together, and I've reversed the orientation on one of them. There's the same manipulation we made for Chern-Simons theory. But because I'm assuming sigma tilde is a small variation, this surface I've built here is the boundary of is the boundary of a three-dimensional region. In M, and since df is equal to 0, d of f is the integral of the 3D region of df, and that's 0. So I haven't explained this. I don't think I've explained this super clearly. You might ask, okay, what is a 3D region? What you should think about is I have a one parameter family, sigma of t, which is constant of surfaces, and they all have the same boundary, and t is varying from 0 to 1. And that sweeps out a three-dimensional region whose boundary is this, is the thing I get from gluing this guy to this guy. Okay.
But can't we do the same argument without assuming the variation is little? Because since the boundaries are fixed, we can just...
We can't, and then you want to use the fact that the curvature is quantized?
Oh no, I was just thinking that I mean I have two blobs. I switch one, then I fix them, and then I get a closed surface. I get the integral of d something. So that would be the integral of a over the empty set because that would have no matter.
Yes. Okay. That's right. So that's that. You're absolutely right. That works. I didn't want to say it like that because I wanted to point out that. In this case, that is absolutely correct. I think it's worth noting that anytime we can build a closed Q form from our fields, this argument will hold, and I get, if I integrate over a surface with boundary, that integral doesn't depend on on the surface I've used to fill in. So the reason in this case, as Isa pointed out, you can see it more quickly. But for Yang-Mills theory, here we have two different closed Q forms, F and star F. And it's not, well, F is D of something, but star F is not, at least not obviously. So for Yang-Mills theory, I wanted to point out that there's two different line defects you can build in exactly this way. Mills, there are two natural defects, which are kind of loop operators. So one is if K is a region in a 4 manifold, we choose K to be the boundary of sigma. So and then we define the Wilson loop to be the exponential of the integral of sigma of the curvature. And the 't Hooft loop okay, so the nice fact about Yang-Mills theory is because the curvature and its hot star are both closed, each of these guys doesn't change if I vary the surface. So if I vary sigma, we have the same argument we just explained. Okay. Any questions? And this is another point at which I'm going off topic, but yes?
Yeah, so this would still be a trivial operator in Schoen's right?
This Wilson line?
Yeah.
Oh, if I can fill in my surface?
Yeah.
So I imagine you're saying that, like, if my gauge field extends across this guy, it must be trivial. That's true. However, I think, as we'll see in a minute, suppose I have one knot like that, and it's just a circle. Because I can fill it in by a disk, the expectation value of that must be 0. But because my gauge field extends across the disk, and all gauge fields in the disk which have 0 curvature are gauge trivial. But something interesting happens if I have two knots which are linked. If I treat one at a time, I can define an observable in this way, but I can't simultaneously make them trivial. So the correlation function between these two guys is non-trivial. On the other hand, with the other definition of Wilson loop, where I just exponentiate the integral, there's no particular reason for that to be trivial if my circle cannot be filled in.
Is there any meaning to the fact that Wilson loops seem to be independent of sigma without making use of the equations of motion, while the Hooke loops are independent of sigma only on shell?
That's a really good question. So this is related to the following fact called electromagnetic duality, which is if we take Maxwell's equations, which is dFA equals 0 and d star FA equals 0, and we want to write them as a Lagrangian, one way to do it is to write, let's assume that there is a potential where F is dA. And that leads to the standard formulation. But that privileges electric things over magnetic things. The other way to do it is, let's assume there's a potential, so star F is dA. And that's kind of the dual formulation. So it turns out that even at the quantum level, there's a symmetry for U1 Yang-Mills theory. So I can present it in two equivalent ways. One as A is a fundamental field. Another is there's a different fundamental field, D of which is star F. So in one formulation, where F is dA, the Bianchi identity is obvious, and d star F equals 0 is the equations of motion. In the other formulation, d star F equals 0 is the Bianchi identity. And the other equation is the non-obvious one. So I think it's important to treat these equations symmetrically. And for these Wilson and Hooke loops, this symmetry of Yang-Mills theory, well, it has the feature, it exchanges the coupling constant to 1 over the coupling constant, and it switches Wilson and Hooke loops.
Yeah, sort of just like terminology question. Like, are there Wilson lines that are not loops? Like, you've been using them sort of the same way.
Yes. So if you have a Wilson line which is not a loop, you have to think about what happens at the boundaries to make it gauge invariant. So that's a little more tricky. Maybe it goes off to infinity, and at infinity, your gauge symmetry is broken, and then the Hilbert space gets modified where the line ends. But so there certainly are.
Are there criteria to decide for what gauge groups and like dimensions of manifolds can be defined gauge invariant Wilson loop operators?
So you're saying if I take Yang-Mills theory and an arbitrary manifold, you mean, or?
Yeah, arbitrary dimensions and different gauge groups. So to what extent can we define such gauge invariant operators?
Right. So you can always define a gauge invariant Wilson line operator for a non-abelian group, but you need to choose a representation of that group. And I haven't written, the formula is similar to this one, just a little bit more complicated. It involves a path-ordered exponential, but I thought I might discuss that next time.
And also in the first proof that we made for the gauge invariance, we do not make use of the equations of motion at all.
Of Chern-Simons theory. That's right. Yeah, it's a good point. So the Wilson loop is a gauge invariant quantity for any gauge theory, because I did not use the equations of motion. I just used the way my fields transform So it defines a gauge invariant operator in Yang-Mills theory in any dimension. For the second proof, we also didn't use the equations of motion. We used the Bianchi identity. Okay, where were we? So now let's take and K2 inside of R3. And I want to do a calculation relating the expectation value of the Wilson loops to something called the Gauss linking number, which we kind of hinted at over there. So we're going to take my group, the OR. This is really the same as U1, but we only allow small gauge transformations. Is one way to think about it. The reason is, we saw above, if I wanted this operator to be gauge invariant, it was important that I exponentiated it with the correct coefficient, because if I took a large transformation, the thing inside the exponential shifted by an integer. But here, for this calculation, I want to take the logarithm of that, which will shift by an integer under a large gauge transformation, so I want to exclude those. So with this hypothesis, then the integral over a naught is gauge invariant. So then you can ask, so question, if K1, K2 inside of OR3 are two knots which don't touch each other, what is the correlation function? So this expression is equal to the path integral over all my gauge fields of e to the Chern-Simons action, appropriately normalized, and the operators I'm measuring are the integral along these knots. And the theorem is that this is the Gauss linking number. So I don't expect you to really know exactly what this is. So I'm going to explain what it is.
So can I ask a question?
Mm-hmm.
So one wouldn't be able to do that sort of thing with tooth lines, right? Because, right?
Take this logarithm.
Because what I was thinking is that now that we're integrating overall gauge fields, we're not asking for unshelledness. So.
No, but the on-shell condition, I think it's kind of a misunderstanding that the on-shell condition just vanishes at the quantum level. At the quantum level, on-shell means things are divergences of the functional measure. So if I was studying Yang-Mills theory, and I built an operator just from, say, if I built an operator from D star F in Yang-Mills theory, something which vanished on shell, it would also vanish at the quantum level, because it's the divergence. It's a divergence in the functional measure, so its integral against any operator vanishes. I think you know this already when you study quantum mechanics, right? So in quantum mechanics, you know I can measure position. I can measure the first derivative of position. The second derivative is vanishes because the equations of motion in classical mechanics. But you don't treat the second derivative of position as an independent quantity at the quantum level either. Only position and momentum survive at the quantum level. Okay, so what is the Gauss linking number? So we have K1 of theta 1, which is in OR3. So theta 1 goes from 0 to 2 pi. And similarly, we have K2 of theta 2. So I'm going to define alpha of theta 1, theta 2 to be, I'll write a formula. So I'll try to draw a picture. I don't know if we're good at pictures. So I'm taking one point on this knot and one point in this one. The knots never actually touch each other. And then I'm drawing the vector that connects one with the other. That's this vector here. And then I'm normalizing it so it has unit length. So alpha of theta 1, theta 2 is in the 2 sphere. So we can view alpha as a map from the product of two circles to the 2 sphere. As my 2 points theta I vary, this torus will hit various points of the 2 sphere. So the quantity we're going to compute is a kind of like a winding number. Normally for winding numbers, we have a circle mapping to a circle, and how many times does it wind around? It's a little more tricky because we have a torus mapping to a sphere. But there is a notion of how many times does it wrap the sphere. And the way you define that is by introducing a measure on the sphere. So we choose omega, which is a 2 form in S2, with the integral over S2 of omega equals 1. So for example, if I get the normalization right, omega could be 1 over 16 pi epsilon I j k x I dx j dx k. So this expression is a 3 form on OR3, and then I restrict it to the 2 sphere. You can, if you want to ask what is the integral of this, you say that's the same as the integral of d of it over a ball. D of this is 6 over 16 pi times dx1, dx2, dx3. And the integral of that should be 1 if you correctly compute the volume of the ball. Okay, so we choose such an omega. And then the linking number is simply the integral over S1 times S1 of the pullback of omega. integral S1 times S1 of alpha star of omega. Okay, so there's two important points about this. Firstly, this does not change if I change omega is changed to something to d of a 1 form. Because the integral of alpha star omega is the integral of, well, so it's the variation. The integral of alpha star d chi is the integral of d of alpha star chi is equal to 0. As a torus has no boundary. And the second important point making a mess of this. The second important point is that if I wiggle my knots a little bit, this also doesn't change. Now, Chern-Simons theory is defined without reference to a metric. So any expectation values I choose of my knots won't change if I change their position, because it's invariant under diffeomorphisms. And I can change their position using diffeomorphisms. And we can see that if I move my knots a little bit without introducing any crossings, this expression does not change. So 2, if we vary the knots, say we introduce k1 of t, theta 1, where t ranges from 0 to 1, and k1 of t theta 1 never touches the other knot, k2. So I'm just moving this guy a little bit so that it never touches the other one. Then the linking number does not change. So this is because as we can consider, there's a map alpha t theta 1 theta 2 from S1 times S from the interval times S1 times S1 to S2, where this interval has coordinate t. And I can just do the same thing, the integral over 0, 1 times S1 of d of alpha star omega, where this is the 3-variable version. Well, this is 0 because this is the integral alpha star d omega. Omega was a 2 form in the 2-sphere, so d of it was a 3 form, and therefore had to be 0 because it's a manifold of dimension 2. So now we use Stokes' theorem to see this integral has two boundaries. This manifold has 2 boundary components. And because the integrand here vanishes, the contribution from the boundaries must be the same. So the integral over 0 times S1 of alpha star omega is equal to the integral of 1 times S1 of alpha star omega, so that the linking number at t equals 0 and equals 1 is the same. Oh, okay, I think maybe I went a little faster though, but are there any questions?
Is the correlation function like non-zero only for like links or also for non-trivial knots?
It's non-zero for non-trivial knots, but it's much harder to understand it because the reason is there's a quite subtle phenomenon by which the invariance you get for a non-trivial knot is not quite a topological invariant. It depends on a little piece of extra data called a framing of the knot. And you see that once you try to study just the expectation value of a knot. It might help to realize that what I'm drawing here, this RO, I'm integrating something from over one position here and one position here. And the integrand is literally the propagator of Chern-Simons theory, which is why this appears. So now if I had some interesting knot, and I found this kind of thing where I had a propagator connecting to itself, there's some kind of issues with the UV, some kind of UV issues which are regularized by sliding the knot off itself, and you get the linking of the knot with itself. But you have to choose a way to slide it off itself. And there's a bunch of different ways of doing that. So it's a slightly subtle issue.
Are we going to see this?
Yes, I hope so. Yeah, I wanted to do this because I asked you to look at the linking number in the tutorial this afternoon. Any other questions? So there's one last thing that's kind of fun. I introduced these Wilson and 't Hooft lines in 40 Young-Mills theory because one reason is a kind of nice result of a 't Hooft that says the commutator of these operators in the operator algebra is again the linking number. If I take K1, K2 inside of OR3, and I put a Wilson line, a K1, and then a 't Hooft line, K2, when I view them as operators, in quantum U1 Young-Mills theory, then the commutator is something like the exponential of the linking number. Another way to do it is if I take sigma inside of OR3, the boundary and some knot in OR3, then I can look at a Wilson line on K. So I can look at the operator, which is the integral of the gauge field over K, and another operator, which is the integral over the surface of star F. And I can commute them. And what you find is the linking number of k on the boundary of sigma. So yeah, I'm mentioning this just to point out that these kind of fun topological things do play a role in real physics. And 't Hooft was interested in all of this because he wanted to study confinement. 't Hooft lines play an important role in the study of confinement. Okay, so I'll stop there.